little bit about fuel quality. So I think I might have shown this slide already to you, but just regarding the fuel quality. So in principle, this road transport fuels that you find in European Union, so there are certain quality requirements that those have to fulfill. And there are also these standards or these certain rules and recommendations behind there, so it's not completely random. The primary purpose is, of course, of the quality requirements is to protect the environment and also us humans, our health, but often it's maybe not self-evident, but also the fuel quality standards and rules are to guarantee that the vehicles, the cars that we that use the gasoline or the fuel, so those work safely, the engines will not break, and also the exhaust gas after treatment equipment will work as planned. So it's a combination of like different aspects. And common ideas behind is that the fuel quality should be such that it aims reduction in greenhouse gases and also prevention of air pollutants like NOx, hydrocarbons, particulate matter, etc. And the second point here, it's quite important from the consumer perspective. So it guarantees kind of that if you fuel your car with diesel, so it's compatible with the cars all over the Europe. So there one would not expect to run into any technical problems or breakdown of equipment due to the fact that you fueled your car in France or in Finland or somewhere else within the Europe. Also, these standards that exist can be slightly different, like outside Europe, for example, in the North America and other countries around the world. So these are not necessarily totally the same, but quite similar, at least in the Western countries. So-called fuel quality directive applies to these commercially sold fuels like petrol, diesel, and also the biofuel. And if you are interested, so you can take a look at this fuel quality directive. I have taken some slides which open up things that the fuel quality directive specifies, but that will come later. But in this fuel quality directive, there are specifications for different fuels like petrol, diesel, so the biocomponents that have been blended into these fuels. And there's a kind of a list, you will see this in a very short while, but a list of parameters. There are a set of minimum and maximum levels, and the parameter values can, of course, vary within these limits, or sometimes there is just a minimum limit, sometimes only maximum limit, depending on the parameter. Also, there are limits for pollutants. These are not actually in the fuel, but those come in the combustion process while the engine is running, so it will become it's in the exhaust gas, so it's not in the fuel itself, but the origin comes from either fuel or from engine and after treatment system performance. Okay, here is a small table listing the certain parameter or these 16 parameters for petrol engine, petrol fuels. And you take a look at here. So here, what you'll see here is on the left-hand side, there is the particular parameter, for example, octane number or research octane number, or let's say amount of certain chemicals like aromatics, olefins, or oxygenates, ethanol, for example. Then you'll see the given, it's like quite common that in standards or these rules, it's specified so in this type of way. So here is also the given units and the minimum and maximum values. So you'll notice that, for example, octane rating or number has only minimum values here. So then you'll see that the hydrocarbon contents have basically only maximum values, and the same applies to these other parameters, for example, sulfur, lead, manganese, and so on. The sulfur content is quite low nowadays, and it's basically previously when the sulfur content in the fuels were higher, so we had this acid rain related problems. Now that is not such a big concern anymore. But for example, in this, at least outside Europe, so the shipping industry, you can use still quite high sulfur containing fuel. Lead has been added to gasoline or to petrol, but I think in Finland, leaded gasoline was sold when I was a child, so it's like it has been basically banned for 40 years or something like that. The problem with lead is that it enhances the engine performance, so it has beneficial effects in terms of the engine, but like you know that lead is a heavy metal and environmental poison, so it's problematic to us humans and nature environment. And that's probably not the reason why it was banned or why the maximum concentration level is so low. The real reason behind is that when the environmental concerns rose, and they started in California in the US, so they started to reduce hydrocarbon emissions from the tailpipe, and that was used with the catalytic converter. And in that catalytic converter, there are certain components, particularly platinum metal, that converts or oxidizes the hydrocarbons very easily, but the lead metal is a catalyst poison. And if you use leaded fuel, it will destroy the catalytic converter quite fast. And that's probably the biggest reason why leaded fuel is not anymore commercially available. I think in aviation industry, it's still being used, not in all airplanes, but at least some. Then this similar table for diesel, it's a bit shorter, but instead of octane number in diesel, there is a similar number called cetane number. I will have a few slides just shortly showing what's the difference or what is meant by this, but it's related to the combustion of these fuels, so ignition and such kind of things. And it tells the higher the cetane number, higher the octane number, usually also the fuel is expensiver. And what else? There is also the sulfur limit to diesel fuels, and there is also the biocomponent blending limit, so of these fatty acid methyl ester content. So this is the traditional biofuel. During this course, we also take a look at the other biofuel, which is a bit more technically advanced, and these are these hydrogenated or HVOs. So hydrotreated vegetable oils, that their performance is much better, and those can be used as such without any fossil components. But this can be added maximum 7 volume% into the current fossil-based diesel that we have in today's gasolines or the petrol stations available. Also, some components like manganese has been regulated. The same goes with aromatic hydrocarbons. Also for the petrol, aromatic hydrocarbons were limited. And the reason there is that aromatics are quite good fuels. They burn nicely and give plenty of energy, but the unburned hydrocarbons like benzene are carcinogenic and are quite a big health threat, at least in larger quantities. So therefore, those are regulated. And here is a list. I took some of the today's material from the Handbook of Petroleum Technology. So if you want to study more in depth these topics that we cover today, so can access probably this via the university's library or something, and find out much more information about this. But this is just a reminder that the petrol and also the diesel that we are currently, those are the most common fuels used, at least in the traveling or passenger cars and such. So there aren't only the energy-giving hydrocarbons in that commercially sold fuel, but it contains additives, and here's a list of those. If you are wondering why I'm having these breaks in my talk, is that I get this info bar on top of the material. I cannot see the slides properly. And that will not show to you, but blocking my view only. So additives in gasoline or petrol, you can find quite many things. That the idea is that they improve the performance of the fuel, or they'll prevent unwanted things from happening, like let's say corrosion in the engine and such kind of things. So this is just to give you an idea that quite many things are added in the fuel, and like the name additive tells, so it means that there are small quantities of these. These are not the main components in the fuel, but their amount and purpose is kind of designed to meet certain quality requirements, as I have highlighted here. So those are not randomly put there. Similar list for diesel. This is a bit perhaps longer in terms of what is added in the diesel fuel. The last one is interesting in that biocides are added to diesel to kill bacteria in the fuel system. I don't know if any of you has a boat or is sailing or anyway interested in boats. So there the big problem has been in the, let's say, 10 or 15 years now, that if you have these FAME, fatty acid methyl ester components, like I said here, that there is the diesel has the biocomponent FAME, or fatty acid methyl ester. So it's components that the microbes also like, and when it's added to these fuels, so it's quite common that when you refuel your boat, so or there is some other leak in the system, so you'll get seawater in the system, and when there is the two-phase mixture of the diesel and the water phase, so this bacteria starts to feel comfortable, and they multiply themselves in that diesel water mixture, and it looks something like this star-like black material, and it's then, of course, when it's increasing in amount, so it's blocking the fuel system and preventing the engine from running properly. And there have been quite big problems with this. So therefore, if you are a sailor or if you have a diesel engine in your boat, so you prefer using diesels that have not any biocomponents blended in those. So just a peculiar detail regarding this. So this is the long list. So there was also like the EU fuel quality requirements. So the fuel has to be compatible with the engine, and that's self-evident. So if it's not, it will end up breaking the engine or causing some problems. That's not wanted. Also, the after-treatment units have to tolerate the fuels and the components in the fuel. So this whole system has been like, how to say, there is kind of a counterplay, or these are interconnected. So the type of the fuel, so it has been fixed and set in these standards and in these rules. The engines have been designed so that it operates and in optimum way with these current fuels. And also the after treatment comes from the fact that the emissions are controlled, and if the car manufacturers want to meet the emission limits, so they cannot do it by just optimizing the engine or selecting the fuel, but they also need to do after treatment for the exhaust gases. And therefore this is kind of a marriage of three, in a way, that there are three components that have to work together. This I already mentioned, that there are blending limits. So this is one way of fighting the global warming and reducing this carbon monoxide, fossil-based carbon monoxide emissions, that the biocomponents are added into the sold petrol and diesel. FAME is used in the diesel, like mentioned already multiple times, but currently bioethanol is used in the petrol. And there are, at least in Finland, we sold this 98 octane, which has E5, so 5% ethanol, and then we have the 95 octane that contains 10%, maximum 10% ethanol as the biocomponent. So this comes from the fuel directive and kind of from the standards as well. This is very old table. I have copied it for years ago. There is only one thing or few things that I want you to take a look. So there are different fuels, and this came. The interesting thing perhaps here is that here are these common renewable fuels like ethanol. It's the lowest row in the table. So the energy densities vary, and it happens to be that the renewable alcohols that are on the table, the energy density is slightly lower, meaning that with the same amount of liters, you get less mileage with the bio if it would be 100% bio component in. Also, some of these like air to fuel ratio and the octane ratings can vary.
Ciao cara. Ciao. Are you
Ciao.
staying? Yes. Alle 7? I don't know. Now I work. And when I finish. Scusa, cara. No, I think
Okay. Yeah, and the thing why I have this here is
Io vedo anche se trovo qualcos'altro. Se lo trovo,
I think
chiamo
I
direttamente e sento.
try to
Scusami Maria Rita, credo ci sia il
close the
microfono
microphone.
acceso.
Look for.
Okay, thank you. So what I was from this table is important properties, water solubility. So we know that these traditional fossil-based gasoline or petrol and diesel are not water soluble. So that's kind of a good property. So if you have water impurities in your fuel, so those will separate as own phase or a water phase usually at the bottom of the fuel tank. But the thing, because water will cause problems in the engine and in the combustion and so on. But when we add there these bio components like ethanol, so ethanol is like from alcohol products, so you can mix it in all proportions, so it's completely water soluble. So it will absorb, for example, moisture from the air, and the water content will gradually rise, and this causes problems eventually. Butanol is a slightly longer chain alcohol than ethanol, and it's slightly water soluble, but in any case, so this comes also in the FAME, so fatty acid methyl ester as this biodiesel component. So it's slightly water soluble, and some of the stability problems and also these microbial growth problems come from the water solubility of that particular chemical. I will not tell you much about these. It was just to highlight some of the things that are important, perhaps for these are also important for the optimal performance of the engine and are related to the fuel itself. So there is for each fuel certain air to fuel ratio, which is kind of the stoichiometric amount of oxygen needed to combust completely the fuel. And the engine can be run with the excess of oxygen or with the slight, so that there is not enough oxygen. So you can vary the amount of air compared to the fuel, and this air to fuel ratio is a measure of that. And this has particular importance for the after treatment catalytic converter. If there is excess of oxygen, you run in the oxidizing conditions. If there is lack of oxygen, you run under reducing conditions. And a few words about that soon. This was also mentioned, the octane rating or octane number. So it's a property that describes something about how how the fuel will burn in the engine. And the research octane number is often connected to petrol or gasoline, and then the cetane number is connected to the diesel fuels. This is also related to the difference in these two engines. Of course, you can determine the number for both for one single fuel. So octane number basically is related to standard component or standard mixture of isooctane and heptane, how it performs in the engine compared to the actual fuel. And this maybe tells the last bullet point here that if the petrol that you'll use has the same knocking characteristics as 90% isooctane, 10% heptane, so then the octane rating is set to be 90. And for example, in Finland, we sold currently two types of petrol, 95 and 98 octane ones. So that means that 95 octane petrol has 95 comparable to mixture of 95% isooctane and 5% heptane. And this can be measured in a laboratory test bed, how is the unknown biofuel or the fuel that we want to determine what's the octane rating of that particular fuel. I don't know if I may make any sense with this, but hopefully. Cetane number is important for diesel fuels, and it also the higher the number, usually the expensiver, and one could say better the diesel fuel is. I will not go into details, but if you on your own time, you can watch, for example, this one YouTube video that explains what the cetane number is about. Tells, I think on the next slide there is, so it tells something about the ignition delay, but I will not go into details with this. So here's some numbers for gasoline and diesel, which are those fuel standard codings or numbers. There are a long list of different standards for different fuels, so this is not any exhaustive or complete list. Important thing with this standardization is, in principle, like you saw those lists of parameters and minimum and maximum limits for certain concentration of components or octane ratings or cetane numbers, etc. So in principle, that this particular commercial fuel, so there are quite a number of criteria that the fuel has to fulfill before it complies with the current standards. And already 20 years ago, when I started to do research in this biofuel field, so it became clear, or there was already at that time talk that we should develop standardized biofuels or standards for particular biofuels in order for those to be commercially usable. And that same is true still today. And this is just copy paste from the EU's web page, where they claim that they are committed to develop these biofuel standards. Say something about the emissions, and these are related to exhaust gas emissions from gasoline or diesel driven vehicles basically. So regular cars tend to emit these typical pollutants that are listed here. So HC refers to hydrocarbons, so that is the unburned fuel components. CO, carbon monoxide, comes from incomplete combustion, so it's only partially combusted or oxidized carbon. Particulate matter are tiny soot or carbon particles that come from the combustion process. And nitrogen monoxide and nitrogen dioxide tend to form. You cannot avoid those very easily because the oxygen comes from air, and air contains nitrogen as such. So this nitrogen doesn't have to come from the nitrogen containing components in the fuel. It comes from also from the nitrogen from the air. And then the completely oxidized carbon dioxide also is formed, plus water vapor and some minor components. In the old times, there came also this sulfur oxides, but nowadays the sulfur levels are so low in fuels that those are basically not really formed in the combustion, or those are not coming out from the tailpipes of regular cars. The reason why these are regulated and are that these cause health problems, like these nitrogen monoxide and dioxide, often referred as NOx, meaning that it's both of these components. So those are, if you inhale those, so those irritate your lungs and so on. Particulate matter is also bad when you breathe those small tiny particles. Carbon monoxide is basically toxic, so it can kill you if you inhale it too much. And also it's not, maybe, I don't remember, but if it, at least for higher levels of hydrocarbons, so those are not good for your lungs as well. But I'm not going through the adverse effects of these pollutants, but the reason comes from many problems that they cause in city environment. They cause air pollution and secondary pollution. When these will react with, let's say, moisture or other components in the air, they can generate this smog or acid rain and things like that, depending a little bit on the component. This slide is quite old, but still relevant to illustrate the point in principle. So the emission legislation or control of emissions have developed in last 30 decades or so. And it started, you should not look at these as absolute values, but what you see some kind of trend here is that in the old days, the limits were higher and became tighter and more stringent when we come towards our times. And in Europe, these emission limits and standards, so these were called these different Euro, starting from EU1 or Euro 1 until Euro 6, that is currently for passenger and diesel cars, I think. And this applies, of course, to the new cars that come out from the car manufacturer. So you can still run these old cars, but the new standards apply to those that are manufactured. And I noticed here's a link if you want to see. So there is also new Euro 7 limits. This is a proposal, but in any case, it's probably coming sooner or later. So the limits become tighter and tighter as time goes by. And also you noticed here that in the early days, so there were limits for carbon monoxide and then this THCs, total hydrocarbons, and NOx. And then in the Euro 2, these were the only ones, but a little bit lower limits. Then here the black bar, it becomes also this NOx separately, and so on and so on. And this, of course, these are the limits that have been set by the European Union. And the car, in simple way, the car manufacturers have to comply with these limits. So these limits cannot be met without changes in the engine, changes without implementing these after treatment technologies that will purify the exhaust gases and so on. And eventually what comes out is better air quality in the cities, at least. That's like outcome, basically. Nowadays, there are also carbon dioxide emission limits for cars being manufactured. This is not really visible from this particular graph, but the way how these standards are met, so there are, of course, several technical details and things that can be done. I have here few examples that have been implemented, and depending, of course, if the methods are different or were different like 30 years ago compared to what is now required from a new car entering the market, let's say this year or next year's, when the Euro 7 limits might be in place. So what you can do, of course, to reduce emissions is first of all to modify the engine, so how it's working and so on, so that it will not generate so much of these pollutants. And if that is usually not enough, so you can implement this so-called after treatment equipment. I'll show you soon what these are, or at least some examples of those. And more common is perhaps to apply many things in order to reach this desired outcome in exhaust or emission reduction. So it's a combination of various things, not just these two separately, but modifications and tiny things all together. These are maybe not that relevant to passenger cars, but in principle for some larger vehicles, you might do retrofitting. You can repower something with like basically changing or replacing the engine. That's of course not really relevant for regular passenger cars and so on. But if you have something bigger, like excavators or some other units, so maybe these could make sense. You can also comply or try to reduce emissions by using these alternative or different fuels. So you can refuel your, let's say, vehicle, and at least still, like, I don't know in countries where you come from, but in Finland, so if you have gasoline driven vehicles, so you can modify it slightly so that instead of running with gasoline or petroleum, it can run with, for example, ethanol or this 85 ethanol, 15% gasoline mixture, and so on. But these probably are some ways how you can try to reduce your car's emissions. The chemistry behind there, so there are two factors like thermodynamics and how fast the equilibrium is obtained. And basically, if you have these pollutants forming there, so or remaining after combustion, so if there is unburnt fuel, so in principle the equilibrium would result in carbon dioxide and water. The same applies for the carbon monoxide, so it would be converted to CO2, and also the nitrogen containing oxides would thermodynamically convert to N2 or nitrogen, and so on. CO2 will be just CO2 based on thermodynamic arguments. So basically, if we would allow enough time for the engine and for the exhaust gas system, so these pollutants would probably in 10,000 years or million years convert to these unharmful components, but that's of course not acceptable. So if we want to speed up the process, so we use catalytic materials. The catalytic materials make the reactions approach the equilibrium faster. I think none of you had chemistry background, but in any case, here are the two reactions that the combustion is generally called an oxidation reaction, and it can take place. Here are some reaction equations for the oxidation. So CH is hydrocarbon. It combines with stoichiometric amount of oxygen, and you get carbon dioxide from each carbon atom, and you get like water molecule from two of hydrogen molecules. That's the complete combustion. And then if there's incomplete combustion, so you tend to get carbon monoxide and water, but well, and some other reactions as well. But we will not go into this now. The other thing what can happen is it's a reduction reaction. That is like opposite to the oxidation. So if something oxidizes, so if you reduce it, it goes to the other direction. But what I said about the speed of this transition towards equilibrium, so the catalysts can help. And if you apply catalytic material, so the reactions can happen faster. So to put it in a very, very simplified way. In these exhaust gas after treatment, or these catalytic converters, so often these noble metals are the most catalytically active ones. And if we are interested in oxidizing these partially oxidized components. So often this palladium and platinum are the best catalytic materials, and you can find them in the oxidation catalysts. If you need to do reduction reactions that I showed you, so if you want to convert nitrogen monoxide or nitrogen dioxide into N2 nitrogen, so you need to reduce it, and there rhodium would be perhaps the best catalytic metal to do that. These palladium, platinum, rhodium, these are noble metals which are very expensive, like some of them are much expensiver than gold. So it's of course problematic in that sense that one would not want to use too much of it. And I will not go into the catalyst design very much, but keep in mind that these catalytic converters in cars, so they contain small amounts of valuable metals, but in any case, at least in Finland, it's sufficient that quite many catalytic converters have been stolen from old cars, because in the old cars there used to have a higher amount of these noble metals. The technology was not that developed, so it's worthwhile to steal them, and maybe, I don't know how much you can get out from it, but few hundreds of euros from one catalytic converter. This slide, which I skipped, is, I don't know if you are familiar with different types of catalytic materials. We come back to that later in this course, because many of these chemical processes that are used to manufacture biofuels, so those are catalytic processes. That means that there are catalytic materials that speed up the process. And there are basically solid catalytic materials, there are homogeneous or liquid catalytic materials, and many more, but we come back to that perhaps later. But in these car exhaust or catalytic converters put into the cars, so the catalytic material is solid metal particles, and they react with the gaseous feed of exhaust gas, and it happens on the surface of that metal particle. And this basically illustrates that phenomena, that the pollutant CO2 will stick on the surface of that catalytic metal. Other components will also stick there. There might be happening some diffusion on the surface, and then also reaction taking place between these adsorbed molecules or intermediates on that surface. Once the reaction takes place, so then the products will desorb from that surface, and this kind of adsorption reaction, this desorption cycles happen on that particular surface. And so these reactions will not take place in gas phase, but on the catalytic material. Petrol or gasoline-driven cars usually have so-called three-way catalytic converter. So it does NOx reduction and hydrocarbon oxidation. So it does two of the opposite things simultaneously, which is kind of surprising, but it works. So it's like heating and cooling at the same time, totally two opposite phenomena, but those tend to happen. So the rhodium metal is speeding up the reduction of NO and NO2, and the platinum metal particles are accelerating the oxidation of unburnt hydrocarbons and partially oxidized carbon dioxide. I think this goes maybe a bit off the topic, but for oxidation, so there has to be oxygen present in the exhaust gas. So it's just that we come back to that in the coming slides. So if we run the car on rich or lean, it influences how the catalytic converter will work. This is very old picture of a catalytic converter in gasoline-driven car, but it's this kind of a monolithic material with tiny channels that the gas is flowing inside these channels, and the walls of these channels are coated with a catalytic material, those metals that are active. There is also some kind of inorganic, like aluminum oxide or some coating that increases the surface area and also incorporates those active metal particles in it, but we don't need to go into details with that. But basically the untreated exhaust gas coming out from the engine runs through this catalytic converter. Those oxidation and reduction reactions take place, and then the cleaned or at least slightly cleaned exhaust gas exits this unit. Very simple, no moving mechanical parts. This lambda or air to fuel ratio I showed already in that previous slide. So it's related to how much the ratio of how much air or oxygen is in there and how much fuel is hydrocarbons is in there. And for this gasoline driven three-way catalyst, the adjustment of the air to fuel ratio is very important for this after treatment unit to work. Therefore, there is oxygen sensor in the system, so that if the air to fuel ratio is wrong, so the engine or it can be then changed and optimized accordingly. So it reacts to this oxygen sensor readings, and it will adjust the lambda value in that unit. But so here's a very old picture, hand drawn, but this will tell you like the operating principle of that three-way catalyst, and we will not worry too much of the details, but when the lambda value is exactly 1, which is in here, so it means that there is that stoichiometric air to fuel ratio, so that there is that much air and that much fuel which is needed for that complete combustion of that fuel. And if there is too much oxygen, So that means there is less fuel. So then you say that you are running lean, the engine. If there is more fuel than oxygen, then you are running in the rich. And basically, the performance varies. So if you take a look at this NOx curve here, so there is a dramatic drop in that NOx conversion if you go close to this lambda value 1. So this is called the operating window. So you have to keep the oxygen air to fuel ratio close to this optimum so that you can simultaneously reduce the nitrogen oxides, and you can also oxidize the hydrocarbons and carbon monoxides. So in order to maintain this optimum situation, so you need that oxygen sensor and continuous control and adjustment of the air to fuel ratio. But that's basically something about the operation principle, but this is linked to the fuel properties and to that mentioned parameter air to fuel ratio. This is the same graph or same information, just put in twice here. Diesel vehicles, this would be also interesting topic to discuss more. However, I just added here that I think for gasoline-driven vehicles, this three-way catalytic converter has worked quite long time, fairly sufficiently well. But in diesel engines, there has been much more development taking place, and the development push or need comes from those tighter EU emission standards or tightening emission standards. And here's a list of some alternatives that you can find in a very old, fairly old diesel car. So you have only the oxidation catalyst after the engine. So you'll see here in this graph what pollutants can be treated with this setup. And you'll see that NOx is not influenced, and also particulate matter is only slightly reduced, but this converts quite well hydrocarbons and carbon monoxide. So these are the things that you'll oxidize and convert in this system. Then there is continuous regeneration technology. There is the difference in the above one is that there is a diesel particulate filter attached to it. So what the filter does, so it captures this PM particulate matter more. So it reduces the small carbon particles in the air. So that's basically just a filter, but in real life, and if you have a diesel car, you'll notice that sometimes the filter is cleaned or it's burned so that the carbon particles disappear from it, and it can again run for some time after doing these burning cycles for that. But this is slightly more advanced. It's just a filter. Then another option is you can little bit improve performance by adding catalytic materials into that filter, but there is not really a huge difference if you compare to these curves. Then, if you have diesel car, you might come up with so-called EGR valve or exhaust gas recirculation. So that's at least what I have in my engine at the moment, because this EGR cooling system has been changed already 2 or 3 times because it can leak and cause a fire in the engine. But that's only the manufacturer's problem. I haven't had to pay for that. But in any case, so the system is what's new in it. So this is basically the same setup as the earlier ones. So there is the oxidation part and there is the filter for the particulate matter. But by recycling this exhaust gas back to the engine, so we can get reduction in the NOx pollution. So this is quite already nicely working, but it doesn't meet these EU6 emission limits, which are very tight when it comes to the NOx pollution. And nowadays, for some years already, so all the new diesel passenger cars have this particular technology that is the most advanced at the moment. So basically, there is the same oxidation filter setup, and then there is, like you see, catalyst that does reduction, afterwards oxidation catalyst, and in order for this whole setup to work, so you need to add urea into your car. So you are not just fueling diesel, but you also are adding from time to time this reducing agent urea. And the reason is that this has to be done in this particular way in order to meet these NOx emission standards. But that's just about these different alternatives. So in summary, for gasoline, if you run with 95 or 98 octane gasoline, so you most probably have this three-way catalytic converter in your car. But if you have a diesel passenger car, so you have some of these setups as the after treatment units. And I think this exhaust gas EGR technology has been in the cars for some 15 years roughly. If you have a less than 10-year-old car, so you probably have this urea technology implemented already in there. And in order to make things, or this just the last point related to these emissions is that there are a lot of catalytic materials in the exhaust gas system. Here are, for example, are oxidation catalyst, reduction catalyst, and oxidation catalyst. So, and typically these catalytic materials can be very sensitive to poisons. So the poison is something that there are different mechanisms, but typically it can adsorb very strongly on that catalytic metal and never leave. So gradually it's blocking the whole catalytic material and then killing the catalyst. That's called catalyst deactivation, or one form of catalyst deactivation. And some of the chemicals or elements, metals and things are very potent poisons. And you need to take that into account when you design the whole system, the engine, the lubricants and the fuels, so that they would not have these catalyst poisons. So this adds an extra level again to the fuel design for the engine design, and also these additives that you put in your fuel. So sulfur, manganese, lead, also some halides can be quite potent poisons. In lubrication oils, previously you might have phosphorus and sulfur, for example. Those are commonly known catalytic poisons. Also, you might end up with some tiny metal particles from that engine wear. So that might also cause catalyst deactivation. So this whole emission control versus fuel quality, also environmental concerns, so it requires quite multidimensional and complex solutions. And in that sense, it's quite understandable that there are these rules and standards and recommendations also regarding the fuel composition. And the standards in particular, so they help the car manufacturers, engine manufacturers, fuel manufacturers, lubricant manufacturers to make products that work well in the current cars. So it's maybe not that stupid idea to have fairly strict and detailed requirements for the fuels and also related things. But that was this part regarding the emissions. So in summary, so basically the current environmental or the emission levels are so low that those can be only met in current vehicles by having proper fuels, optimized engines, and also quite sophisticated exhaust gas after treatment equipment, all working together